Hello, we are going to see the usefulness of the piezometric graph. Here in the flow test, we have created a generator with a flow rate of 500 cubic meters per hour. We see the circulation, the fluid moves, and its pressure variation is given here, according to a color code, whose scale is given below. We stop the test and we color the elements, so we could have fairly precise information on the pressures, only by a color code without looking much further. You can also read the pressures by selecting the objects. Here, at the exit of this pipe, we read 1.22 bars. And at the exit of this element, here we have 2.1 bar. We go from 1.1 to 2. We have an increase in pressure. If we don't think about Bernoulli's relation, this may seem confusing. With the pressure drops and the direction of displacement, we could imagine that the pressure should decrease gradually. Bernoulli teaches us that this is not the case, because for a unit of volume the global energy is always constant. Here we have a speed reduction, produced by the enlargement. So the dynamic pressure which is linked to the speed will drop. And this drop in dynamic pressure will be counterbalanced by an increase in static pressure. Here we can see the effects of these energy variations, generated by the speed variation. But it is not clear where these variations come from. The usefulness of the piezometric graph is to explain, by separating the different component elements, the pressure within the fluid. We show the piezometric graph of this small network. The piezometric graph is selected here, by clicking on this button, which edits the piezometric graph. We will simplify here. We will show, for example, the dynamic pressure and the total energy. At the entrance, here we have the generator. It's that part. A straight pipe, that part there. An enlarged cone, a straight part, an elbow, which is another one here. Another pipe, another elbow, a narrowing which is here, and the outlet which is there. So our section is represented here in the form of a graph, with the inputs and outputs of each element. Here there is an acceleration of the fluid, so the dynamic pressure increases. In this duct of identical section, at the inlet and at the outlet, the dynamic pressure remains stable. Here, we have a widening. The law of continuity tells us that, in a vein of fluid, the flow is conserved. Therefore an increase in section generates a decrease in speed. And a decrease in speed, it is a decrease in dynamic pressure. Here, in these different organs, we always have the same section. So the dynamic pressure remains constant. Here we have a narrowing, therefore an increase in speed. An increase in dynamic pressure, and at the outlet, the pipe has no variation in section. And we see that at the network outlet, the fluid comes out with its dynamic pressure. So let's start with a dynamic pressure of 0, and we end up with a dynamic pressure here of 156,000 pascals. We will now show how the hydrostatic head also intervenes. So we're going to leave the dynamic pressure. Here we see a new line that represents the hydrostatic head. The hydrostatic head is negative if it goes against the progress of the fluid. It is positive if it helps the progress of the fluid. So here in our network, we have an elevation rise from this elbow exit. we will see that the hydrostatic pressure evolves from this elbow. We see it here. The hydrostatic pressure delta between departure and arrival is given here. It is a negative pressure because it is not an increase in energy. It is a sum of negative energy, which will have to be supplied by the pump. We will now see how the head losses evolve. Here we see the load gains and losses. The pressure generator provides pressure, so we observe a load gain. And the crossing of the various organs produces pressure drops up to the outlet. All this modifies the nanometric pressure measurable within the fluid. And we see the different pressure energies, which generate the static pressure within the fluid. At the entrance, at the exit of each organ, we enter with an atmospheric pressure of 0. And we leave with an atmospheric pressure of 0. The small delta that can be observed here, minus 29 pascals, shows the imprecision of the calculation. Under the piezometric graph, we see the data table of the graph. You can see the detail of the values for each element. It's a pretty interesting editing tool to feed a study file. We can modify the scales and give aesthetic effects. Personally, I prefer in 2D, with a proportional scale, but in some cases, it can be interesting to modify this appearance. So here is the end of this tutorial, showing the piezometrics of Mecaflux Pro 3D.